Chapter 17 Notes, Part 2. Last week we were looking at similarities between gravitational force and the electric force. The moon is orbiting around the Earth because the gravitational force is pulling it towards the center, towards the Earth. An electron orbits around a nucleus because the electric force is pulling it towards the center, towards the nucleus. And remember, anything going in a circle goes in a circle because a force pulls it towards the center, and that force is equal to the centripetal force. We also learned that we could rearrange this formula so it is a physical property of the matter times a field, physical property times a field. And we could rewrite these formulas as force equals Q times E or M times G. We're also looking at how to find the potential at a particular point. Remember, there was two different formulas, one for a point charge and one for parallel plates. We also learned about equal potential lines. Anywhere along this line has the same potential because it has the same d, the same distance, and the same field. Anywhere along this line has the same potential because it has the same radius and the same field. We're also looking at how much work does it take to move an object from one plate to the other. Today we're going to look at moving an object between points A and point B inside of a field. So lifting my rock up, I started with this potential energy, I'm ending with this potential energy. We can subtract these potential energies to find the work that's done lifting the rock. I can factor out the mg and rewrite this as mg times the change in height for the work done. Remember, this is also the potential energy that's gaining as you're lifting it up. For the parallel plates, we can do something similar, but I know that E times D is the potential, so I'm going to substitute potential into this formula and then factor out the Q. So our formula becomes Q times the change in potential. Looking at our equal potential lines, we're going from a lower potential to a higher potential, both between the parallel plates and between the gravity field here. The gravity field, I can rearrange this. Remember, we call G times H the potential for the gravity field. So both of these formulas, again, we have the characteristic property times the change in potential. We're also looking at how to find the electric field at a point. We're going to measure this distance to the first charge and use kq over r squared. Then we measure the distance to the second charge and use kq over r squared. And it's the vector sum of these two fields that makes the total field at P. Today I want to show you what that looks like. If I follow the field lines from the first point, this field line is moving in this direction away from point P. And if I follow the field lines towards this negative point, that field line is right along this line. And if I add those two together, moving them head to tail, the sum of those two forces is this one. Last week I had you learn all the patterns for the electric fields. This is our pattern. And if we look right at this point, that tangent line is going perpendicular, right in the direction that we calculated it would be going. So we could do the same thing. We could choose a point Q anywhere and follow that tangent line, and it shows us the direction of the sum of these two vectors being added. New things this week, we'll find the potential at point P. This one works a little bit differently. We start off by finding that distance. The potential formula is kq over r. Then we find this distance from the second one, kq over r again. But since this is a scalar sum, not a vector sum, when we add these, we have to include the plus and minus signs in the formula. And that way we know, are we adding or subtracting these because of the plus and minuses in the formula. This one looks different on the picture. Potentials are equal potential lines. Each one of these lines, as you get farther and farther from the charge, you have a smaller and smaller potential. And this one we have negative potential lines. So at this point P, we have 3 volts along this line and negative 2 volts along this line add together to make 1 volt for our net potential at that point. So for potential, we know it's a scalar. It could be positive or negative. It depends on 1 over r, not 1 over r squared, so it doesn't follow the inverse square law. It's measured in volts, and we're going to define volts as a joule per coulomb. These units need to be all memorized. Last week we defined potential as potential energy per charge. This is where the joule comes from. This is where the coulomb comes from. So how much work does it take to move a charge from infinity to point P? We're going to use a new formula. Work is Q times the change in potential. Now the Q is the point charge that I'm moving up to P. The potential is what's coming from this point. So the work is going to be Q times V final minus V initial. V final is the V at point P here, and V initial is the V at infinity. If I put in infinity for K Q over R, this number becomes 0, which reduces our formula down to Q times V, which is the formula we were saying last week. It was the potential at that point. I can put in KQ over R for this potential, and we get a new formula, KQQ over R. This is the work for moving a test charge from infinity to point P inside this field from this point charge. On your formula sheet, it also says this is equal to U. That's a symbol for potential energy. How much work is done by the field to get the electron to come out the other side? This is similar to the problem we did last week. We know the electron is going to repel from the negative plate here and attract towards the positive plate on this side. So it comes flying through. And in order for a transfer of energy to occur, we're starting with potential going to kinetic. Some work has to be done, and that work is done by the electric field. So our formula here, work is Q times the change in potential. If we look at its final minus initial, the final plate is B, the initial plate is A. So what is the potential at plate B? If I hold this electron right on this plate and let go, nothing happens to it. That means it has no potential energy, and it means that there's no potential at that point. The potential is over here on this side because as soon as I let go, it's going to take off. It has potential energy. So the potential at V is 0, which means our formula reduces down to negative QV. This negative actually shows that the work that I am doing on the electron is negative. Therefore, the work that's done by the field is positive. So let's look at this. How do we know if the work's going to be positive or negative? I have a proton, I have an electron, and I am going to push them from the positive plate towards the negative plate. One of these particles, I am doing work on it, and one of these particles, I'm doing negative work. The way it works is, if the object moves by itself, the work done on it is negative. So that would be the proton. The proton is going to repel from the positive plate and attract to the negative plate. It's going to go all by itself. I don't have to push it. Now the object that has to be pushed with a force, the work done on it is positive. I was doing positive work on the electron. Pushing back the other way, the electron is going to go by itself because it attracts towards the positive plate, and I'm going to have to push the proton this time to make it go the opposite direction. So the force done by the field is always opposite of the work that's done by me. That particle that goes by itself is going by itself because the field is doing work on it. The particle that has to be pushed, I have to do the work on it. So in these formulas, why is it that this field is negative? That negative sign is showing the direction of the field lines. We don't include it when we're using the formulas. It's just like when we're doing the Hooke's law formula said F equals minus K times X. The minus is just showing a direction. It's not part of the field or not part of the force. On your formula sheet, we have some things to go over, so get your formula sheet out. This first formula, I mentioned last week that this front part is equal to K, and if you have the new formula sheet, I think they put the K in there. So this formula becomes KQQ over R squared. The next one on the sheet, the field is the force divided by Q. So if I take this force and divide one of the Q's out, we get KQ over R squared. The next one, U is the symbol for potential energy, and that equals Q times V, or in the case that we've been talking about today, it's Q times the change in potential. And then this is the formula for the point charges. That's going to reduce down to KQQ over R. And the last one here is for the potential. Remember, this front part is K, and then we have Q over R. So KQ over R is the formula for potential. Now all four of these are the formulas for point charges. And these are the formulas that have the K in them. If that formula has a K, it's for a point charge only. You cannot use these with parallel plates. For the summation sign here, the summation sign is reminding us that this is a scalar sum, not a vector sum. And remember, that's why you have to include the plus and minuses in this formula, but not the others. End of notes.